All right, we're diving straight into a really foundational paper today. It's called WebGym, Scaling Training Environments for Visual Web Agents with Realistic Tasks. This is a big collaboration from Microsoft, UIUC, and CMU researchers.
Yeah, and for anyone out there building these kinds of VLMs that have to actually interact with the web, this paper is pretty much mandatory reading. The big takeaway is about the environment, not just making bigger models.
Absolutely. So for that 1-minute summary, that quick hit on what makes this paper so important, there are really 3 things. First is just pure scale. I mean, WebGym is the largest open source training environment we've seen. We're talking nearly 300,000 tasks.
Which is huge. That's about 3 times bigger than any of the prior large-scale setups.
Right. And second is speed.
Efficiency. They really tackled how slow web interaction is for these agents. They built this high-throughput asynchronous rollout system, and it gives them a 4 to 5 times speed up over the normal, synchronous way of doing things. It makes online reinforcement learning actually practical.
And the third insight, which is frankly the one that really turned heads, is the performance they got out of it. They took a relatively small open source model, the Quinn 3 VLM-Instruct 8B, fine-tuned it on WebGym, and the results on auto-distribution tests were just incredible.
They were. We're talking about tasks on websites the model has never, ever seen before. It went from a baseline of, 26.2% success all the way up to 42.9%. And that number, that 42.9%, just blows away proprietary models like GPT-4o at 27.1%, and even GPT-5 Thinking, which only got 29.8%.
That is a massive gap. A smaller open model beating the giants by double-digit points. That's a huge signal about where the work needs to happen. Okay, so let's unpack this. Why is it so hard to train an agent to do these sort of human-like tasks on a live website using standard RL?
Well, it really boils down to a couple of major hurdles that RL is just traditionally not great at handling.
Okay, so what are they?
First, the environment itself. Real websites are what we call non-stationary. The whole layout, the code, the elements, it all changes constantly. A/B testing, redesigns, whatever. So a policy that works perfectly today might be completely broken tomorrow.
And the second problem is just the cost, right? The computational cost.
Exactly. It's not like a text environment where a rollout step is milliseconds. Here, every single step means rendering and then analyzing a high-resolution screenshot. The observation space is massive, data collection is painfully slow, and that makes the usual way of doing rollouts just prohibitively expensive.
And these are visual agents, so they're looking at screenshots, basically trying to mimic how we see and use a browser. Why that approach? Why not just parse the clean HTML or the accessibility tree? It feels like that would be easier.
It might seem easier, but it's all about generalization. When an agent learns from screenshots, it's forced to reason about visual affordances. It learns that, a blue rectangle with some text in it is probably a button no matter what the HTML tag is called.
So it's more robust to changes in the underlying code.
Way more robust. If you rely only on the code structure, a tiny change, like a developer renaming a CSS class, can completely break your agent, even if visually nothing changed. So this visual approach is better for the real world, but it creates that bottleneck in data and rewards that WebGym was built to solve.
Okay, so bottleneck number 1 is the data, the lack of high-quality, diverse training tasks. WebGym solves this with almost 300,000 tasks on over 127,000 websites. I mean, how do they even assemble that?
So they use this really clever strategy of aggregation and then procedural generation. For the breadth, the sheer number of websites, they pulled tasks from 10 well-known benchmarks.
Things like Mind2WebLive and so on.
Exactly. So that gives you this great foundation. It covers that long tail of websites you need for good generalization, but also has enough repetition on common sites to give the RL a strong signal.
Okay, but just aggregating tasks only gets you quantity. How do they get the depth? How do you push the agent to do more than just, click a single button?
Right. And that's the second part, the procedural construction. This is where GPT-4o comes in, and this is, I think, the core innovation on the data side.
How does that work?
So instead of just writing a task, they get the LLM to generate an evaluation rubric first. And this rubric is structured into what they call fact groups. The difficulty level of any task is then just the total number of facts the agent needs to find to complete that rubric.
So difficulty isn't just a guess, it's a hard number. It's measurable.
Precisely. And then if a task is complex enough, say it has at least 2 of these fact groups, and one of them is kind of large, they use the LLM to automatically break it down. It takes that one hard task and decomposes it into several strictly easier subtasks, just by picking different combinations of the fact groups.
Can you walk us through that pianist concert search example? I thought that was really clear.
Yeah, that was a great one. So the original complex task was pianist concert search. That was a difficulty 9. It needed the agent to find 3 different groups of facts: stuff about the pianist's eligibility, details about the musician, and then the actual concert info.
Okay, 3 fact groups.
Right. So by just taking subsets of those 3 groups, the system could automatically generate 5 brand new, simpler tasks, things ranging from difficulty 3 up to 7. And the guarantee you get is that these new tasks are never trivial, but they are always easier than the original, which gives you these dense, high-quality reward signals that are just perfect for RL training.
That procedural generation sounds incredibly powerful. But how do you make sure the evaluation is accurate? I mean, on the open web, an agent might get the right answer, but in a weird way, and a simple check could mark it as a pass, right? That introduces noise.
It introduces a ton of noise, and that's the problem with just having a simple did it succeed judgment. The rubric-based system in WebGym is much more precise. Instead of a simple yes or no, the rubrics list the exact facts that have to be satisfied, and their validation showed this just massively improved accuracy and precision.
But the paper did mention something interesting. It said the LLM-generated rubrics were sometimes overly strict, and it actually hurt recall a little bit. Isn't that a bad thing? If the judge is too harsh, you might be throwing away good training data.
That's a great point, and it seems counterintuitive. Yes, the LLM judge was tough. It might not have given credit for an answer that was technically right, but not formatted perfectly, for instance. But for online RL, that strictness is actually a feature, not a bug.
How so?
Because a very strict conservative rubric gives you a much cleaner, less noisy learning signal. The policy learns the exact boundaries for success. It might reduce the total number of successful trajectories you collect, but the ones you do get are pure gold. They chose precision in the reward signal over raw quantity.
That makes a lot of sense. You're building for robustness. And before we move on, we have to talk about the OD test set, because for anyone listening, this is really the whole point of the paper.
It's the gold standard. It really is. The test set has about 11,167 tasks, and the critical rule is that every single one of those tasks is on a distinct website the model has never seen during training.
Never.
Not once. So there's zero chance the agent is just memorizing layouts or patterns for a specific site. It has to be using general skills. That 42.9% success rate is a measure of pure, honest-to-God generalization.
Okay, so that brings us to the second big innovation: speed. Browser simulation is just famously painfully slow. Now that we have this huge data set, we need a system that can actually get through it. How do they get that 4 to 5 times speed up with this asynchronous system?
Yeah, the enemy here is synchronization. It leads to this really inefficient hardware use they call burst idle.
Burst idle. So like a bunch of work happens and then nothing.
Exactly. Think about a normal synchronous system with, say, 100 parallel browsers. At the end of every step, all the fast browser sessions that finish their action have to stop and wait. They just sit there, idle, waiting for the one single slowest session to finally finish rendering some complex page.
So 99 of my expensive GPUs could be just sitting there, waiting on one slow CPU process. That sounds like a terrible waste of money.
It's a massive waste. You get these huge spikes of GPU usage, then deep valleys of nothing. The asynchronous solution fixes this by completely decoupling the whole process. They use a server-client architecture. The server runs the browsers, that's the CPU-heavy part. The client runs the agent, that's the GPU-heavy VLM inference.
And how does just decoupling them get rid of the waiting?
Because they communicate through queues. There's no step-level barrier. As soon as a browser is ready for the agent's next move, it sends the observation to the client queue. The GPU grabs it, processes it, sends the action back to the server queue. New tasks just start immediately whenever a resource is free. The CPUs are always working, the GPUs are always working. Nobody waits for anyone else.
That sounds smart, but they mention another optimization on top of that, these operation-specific local queues. Why was that extra step necessary?
Because even in a setup like this, you can still get bottlenecks. Imagine you suddenly get a flood of really complex navigation tasks. Those are very CPU-bound. If they all jam up the main queue, they could end up blocking simpler, faster operations, like just taking a screenshot, from getting to the GPU.
So fast jobs get stuck in line behind slow jobs, even if the resources are free.
Precisely. So by creating separate queues, separate lanes for navigation, for screenshots, for executing actions, they make sure there's this continuous balanced flow. It's just good engineering, and it's why their system scales almost perfectly linearly as they add more GPUs. They collected 1,800 full trajectories in just 30 minutes. The speed up is very real.
So, with the environment built and the speed problem solved, we get the final piece, the agent training. They use a pretty simple reinforced style algorithm, which is basically online filtered behavior cloning. But even that required a couple of major hacks to work on the web. Let's start with memory.
Right. You have to think of these web tasks as POMDPs, partially observable Markov decision processes. For any long task, like comparing products across 3 different pages, the agent has to remember what it saw. Old models would use a tiny windowed history, like the last 3 screenshots.
And it would just forget everything before that.
It would suffer catastrophic forgetting. It gets stuck in loops because it can't remember it already clicked that button.
So how do they solve that long-term state tracking?
They did something really clever. They introduced a dedicated memory prompt. At every single step, they forced the VLM to respond not just with an action, but with an updated textual summary of its memory in a JSON format. This text output basically becomes its own compressed state buffer.
So it's using its own text generation ability to create a running log of what it's done and seen.
Exactly. It's remembering, I found the price on page 1, or I added the item to the cart. And their ablations showed this gave them a huge performance boost on long horizon tasks.
That's a great trick. What was the second big intervention?
The second was just tackling simple action repetition. Even with the memory, the base model would often get stuck just clicking the same button over and over on the same screen. It's a massive waste of samples. So they added a simple repetition penalty filter. If the agent takes an action and the next screenshot is identical to the last one,
Meaning nothing happened.
meaning the action did nothing, that step gets filtered out. It just forces the agent to stop wasting time on useless or circular paths, which makes the training way more efficient.
Okay, let's get into the scaling ablations. This is where we see exactly what produced that 42.9% result. They looked at breadth, size versus depth, and then horizon control. What did they learn about the breadth of domains?
It proved to be absolutely critical for ode generalization. They ran a test where they cut the number of subdomains in half, and the result was immediate. Learning slowed down, and the final success rate dropped from 34.5% all the way to 31.0%. It just confirms that seeing a huge variety of website layouts is the single most important thing for learning transferable skills.
And what about the mix of tasks? Should we just be training these agents on the hardest problems we can find?
No, actually, the results really support a balanced approach. Uniform sampling, a big pool of easy tasks mixed with some medium and hard ones, did way better than only using easy tasks or only using hard tasks. The easy tasks spread across all those websites are what prevents overfitting. But you need the medium and hard tasks to provide the signal to develop more advanced skills. It's a balance.
Diversity for generalization, a balanced mix for capability. Got it. But the single biggest performance jump came from what they called horizon control. They reduced the maximum number of steps the agent was allowed to take. Now that sounds completely backwards. Why would giving the agent less time make it better at solving complex problems?
I know, it feels so counterintuitive. But this is probably the most critical insight for anyone training these agents. They tightened the step budget during training, from a generous 15, 30, 45 steps for easy, medium, and hard tasks down to a much stricter 10, 20, 30. And that tight constraint acts as a powerful regularizer on the policy.
How does that work in practice? What does it force the agent to do?
It forces the agent to learn to be decisive. If you know you only have 10 steps, you can't afford a long, wandering exploration path. You have to learn the shortest, most effective actions. You're incentivized to find the most efficient path right away. And by optimizing for that efficiency during training, the policy learned these incredibly robust, reusable skills that transferred surprisingly well even when they gave it a full budget at test time. It pushed the model to that peak, 42.9%.
That is a phenomenal result. So you have a small open source model that, thanks to this amazing environment, the asynchronous speed and these clever training regularizations, achieves state-of-the-art performance on unseen websites. It's beating proprietary giants by more than 13 points. It's just proof that engineering the environment can give you these massive gains.
Absolutely. It shows that for a long time, the environment was the bottleneck, not necessarily the RL algorithm. Of course, they did highlight that those strict LLM rubrics are an area for future work. They're great for precision, but making them a bit more flexible could improve sample efficiency even more.
Which brings us to a final thought for you to take away. As you think about designing training for your own agents, what does this imply? If putting these tight constraints on the agent, the short time horizon, the strict rubrics, if that's what forces it to learn these fundamental generalizable skills, should we be intentionally hamstringing our agents during training to make them more robust and decisive when it really matters? Is constraint the ultimate mother of generalization?